Hello everyone. I hope everyone is keeping safe themselves during this pandemic situations. Let me introduce myself. I am Kumar. I am MTech graduate in Building Energy Performance from SEPT University, Ahmedabad. So let me introduce my research topic. It's research topic analysis of flow pattern using water table apparatus by varying the model scale. So the outline of today's presentation is broadly classified into 5 parts. So without any delay, let's go to the first part. The first part is the introduction. So background. So what is ventilation? Ventilation is a process of air supply to control contaminants, air contaminants, humidity and temperature of a given place. And why do we need ventilation? Because in today's scenario, people spend 90% of the time indoors, especially at homes or offices. It is important for them to provide acceptable indoor air quality and thermal comfort. However, it is the main issue in evaluating the thermal ventilation performance of a building is due to varying outdoor conditions. In this case, naturally ventilated buildings operate well by providing adequate ventilation rate with acceptable indoor air quality. So a literature study has been conducted to know previous research work on water table. So it is observed that few research works has been conducted on the water table analysis. So these analyses are mostly focused on qualitative and visualization of flow patterns which demonstrated air movement and proposed design strategies. Recent studies has also derived the quantification of these flow patterns. However, the limiting size or the scale has not been recorded in this literature. Hence, it is important to know the scale for which the experiment to be conducted for the water table. So my research question was, what is the effect of model scale on the ventilation metrics using in the water table apparatus? And my objective was to simulate different model scales in water table and understand its effect. And as of any research, this research has few limitations, like effect of wall thickness, internal partitions has not been considered, and water table helps in only prediction of 2D air movement. So my methodology is broadly classified in 3 parts. First part was the literature review. Second was the photographic analysis, where the data has been extracted for the photographic analysis. And third part was the experimentation, where all the experimentation has been carried out. So the experimental setup. So here you can see the experimental setup as shown in the figure. The model is initially the model is placed at the center of the model of the work plane, and then the water is pumped, clear water is pumped from one end, and later the color dye is passed from the other from one end of the work plane, which is considered to be as the leeward zone. You can see the water is coming from this zone is considered as the leeward, and this one is the backward zone. So few experiment has been conducted to see the symmetrical analysis of the flow, and also an experiment has been conducted such that to check the flow from each nozzle is uniform. So an experiment has been carried out to establish the relation between the pixel value and the concentration value. So the experiment has been conducted from concentrations varying from 0 grams to 0.15 grams, and a calibration curve has been developed to establish this relation. The curve has been taken such that the R square value is near to the 1. So such that the data points fits absolute to this curve. So here I have used two equations for different concentrations to calculate the pixel values. So the first equation is as shown here, and the second one equation is here, where C is the dye concentration and Px is the pixel value. So next comes the ventilation metrics. Ventilation metrics are basically which are useful in predicting the ventilation performance of a given space. So here I have calculated 3 ventilation metrics. First one is the percentage dead spots. Percentage dead spots define the lack of proper mixing, where there is no mixing of air occurs, and it is calculated by the formula as shown here. The percentage dead spots are more in the room then the room is poorly ventilated, and when the percentage of dead spots is low, the room is properly ventilated. So absolute ventilation efficiency. It is the ventilation ability of quite opposite to the dead spot. It shows how effective room is ventilated. So here's the formula you can see, which is used for calculating the absolute ventilation efficiency. So ACH. ACH is the process of substituting stale indoor air with the fresh outdoor air, or in other words, rate of air changes per hour in a room. So it is used for calculating the mass balance equation is used to calculate this ACH, as shown. The formula is shown here in the presentation. And in order to establish the relationship between the water table and ACH in water table and air, a dimensional analysis has been calculated using the formula here. So I have done experiments for 3 different components. First one is the single side, second one is the adjacent, and third one is the opposite side. And all these configurations are divided into 9 zones for ease of calculation and to see the effect of each zone, how the ventilation is performing. And here you can see the table of this representation of these zones. So different model scales used. Here is the pictorial representation of the different model scales which I use for the experimentation, starting from 1:20 to 1:80, the largest scale. And so let's go to the first part, how the effect of dead spots is shown on this one. Initially, the percentage dead spot is calculated at zonal level because the average concentration value of a room takes the entire room for calculation. So I have calculated for the zone 1, which is LT, which is also left off. So it is observed that the smaller scale values has taken less value to reach a stable time within 7 to 8 minutes, whereas the other scales like 1:20 and other scales have taken 12 to 30 minutes to get stable in the experiment. So later, an average concentration of the room has been used to calculate to see the effect of dead spots. So it is observed that for the scales 1:20 to 1:60, the average difference between them is 1.4%, whereas the scales 1:70 and 1:80 shows the difference of 13% and 17% respectively. So this method has been carried out for the other 2 configurations, and here you can see the differences in the average values of these scales. And from all these 3 configurations, it is observed that the average values of this concentration for all these configurations from scales are low for scales 1:20 to 1:60, whereas the scales 1:70 and 80 shows a vast difference in the average in the slope value, which you can see here clearly. So effect of model scale on ventilation efficiency. As I told before, it is the inverse of dead spot. So you can guess that the room is properly ventilated when the scale is low, and it takes time when the scale is higher for like 1:20. So the same thing is observed for the other 2 scales, adjacent side as well as the opposite side. So let's see the effect of model scale on the ACH. So here the left part indicates the ACH in water and the right one indicates the bar indicates the ACH in air. So here's the configuration for opposite side. Uh, opposite side. So let's comes the adjacent side and the single side. It is observed that for these scales 1:20, 30 and 40, in all the scales, the ACH value seems almost near, but however, it is observed that the ACH values for OS configuration, that is opposite side, is higher than the other 2 configurations. However, in theory, the ACH should not change if the change in all 3 configurations. But however, this change has been observed in the scales. Scales has been observed. There are mainly 2 reasons for this. One is this because the change in the Reynolds number, and other thing is the change in the velocity, because when the velocity increases, the speed increases, which why the smaller scale has higher ventilation rates when compared to the other scale. So conclusion. So Let me conclude for this sector. So the biggest size simulated in this study is 1:20, which is 1:20, which is of 20 by 20 centimeters square. And it is observed that the model scales from 1:20 to 1:60 followed the same trend in terms of metric calculation, ventilation metrics, or while the result showed by 1:70 to 1:80 scale showed a significant variation results in terms of ventilation metrics. For the current water table, which is of 152 by 75 centimeter setup, 1:60 is a minimum scale of model one can opt for conducting experiment. It corresponds to the model size of 6.6 centimeters square. If the study has multiple zones, smaller scales from 1:30 to 1:60 can be preferred without significant difference in the ventilation metrics. I would like to thank you for Priya for giving this opportunity. You can contact me on the email address given below if you have any queries, and hope you all keep stay safe and take care of yourselves. Thank you.